Hey guys, Dr. Cadell, and this is the acid-base titrations lab. So the basic idea in this experiment is you're going to prepare a stock solution of sodium hydroxide. You're going to determine the concentration of sodium hydroxide in that solution, and then you're going to use that solution to determine the concentration of an unknown acid. So the basic chemical equation that describes both parts of this experiment is this one right up here. In this equation it says sodium hydroxide plus some monoprotic acid. HA is just a generic term, and all it means is it's some acid and there's one proton. In other words, the mole-to-mole ratio between the acid and sodium hydroxide is 1 to 1. And this applies to both the first part and the second part of the experiment. So in the first part, we're going to make up our stock solution of sodium hydroxide. And we're not going to be careful with any measurements because it doesn't matter. We're going to get an approximate solution, and then in the first part we do what's called standardize that solution. To do that, the acid in this equation is called KHP. The only thing you really need to know about that is it's also monoprotic, and its molar mass, which I give you in the lab report as well as right here. So what you're going to do is you're going to take 3 beakers or flasks, weigh out some of this KHP. KHP is a solid. You're going to weigh it out into the flasks, add some water, and then you're going to put your stock sodium hydroxide solution into a Buret, which we'll talk about in a minute. And then you're going to react the sodium hydroxide with the acid down in the beaker. And if we can determine, guys, when we've reached what's called the equivalence point, the equivalence point is when you've added exactly enough sodium hydroxide to exactly use up all the acid that's down there in the beaker, but no more. That's nice because if we can do that, and we can, I'll tell you how in a minute, then we know that the moles of sodium hydroxide we've added is equal to the moles of the acid that's down there in the beaker. And this is the general idea in both parts of this experiment. Well, with the first part, okay, it's this solid acid, KHP is what it's called, potassium hydrogen phthalate. And because we weigh it out and we know the molar mass, we can calculate quite easily how many moles of KHP is in each of those beakers. And I take you through that in the lab report, don't worry about that. So knowing the moles of the KHP, we know the moles of sodium hydroxide added because they're the same, it's a 1 to 1 mole ratio. Now, in the first part, this is our goal, to determine the concentration of sodium hydroxide in our stock solution. And remember, molarity, which is what this symbol means, is equal to the moles of the solute divided by the liters of solution. And here the solute is sodium hydroxide. And so what I just described up here is how we find out how many moles of sodium hydroxide we added to that acid. And again, this by finding moles of acid, setting that equal to the moles of sodium hydroxide, that's that number right there. The only other thing we need, guys, to get our answer for the first part is the liters of solution. How much of that sodium hydroxide did we add from the Buret? Well, it's really pretty easy. All we do is we measure that volume with the Buret, which I'm going to describe in just a moment. But all you do is you record the initial volume in the Buret and the final volume. The difference between those two is the volume added. Now, because the Buret we use reads in milliliters, we need liters. So what we're going to do is divide that by 1,000. So over there in red, if you can see that equation there, that's just showing you how to find the bottom part of this equation here. So the liters of solution, which is just the denominator in the equation for the concentration of sodium hydroxide, is real easy. It's just the final volume minus the initial volume, which is going to be in milliliters. These numbers right here, guys, these we read from the Buret, the final, the end volume, and the starting volume. And we divide by 1,000 milliliters per liter. That'll convert it to liters like we need to. All right, so just to make sure this is clear, guys, to get the moles of sodium hydroxide, it's equal to the moles of KHP at that equivalence point, the point at which we've added exactly enough sodium hydroxide to just use up all that acid. To get the moles of KHP, we just take the mass that we weigh out, because we're going to record that, and divide by the molar mass of KHP. That's what this number is, 204.22 grams per mole. And that'll give us our our moles of KHP, which gives us our moles of sodium hydroxide. So it's crucial, guys, that we know when we have added just enough sodium hydroxide solution to exactly use up all the acid and no more, when we're at what's called the equivalence point. Well, the way we're going to do that is we're going to use something called an indicator. A particular indicator we're going to use today is called bromothiamyl blue. It doesn't really matter. There's all kinds, probably hundreds of indicators. But what an indicator does is it changes color at the equivalence point. And the way this one works, many of them work, is they depend upon the pH, how many protons there are in the solution. So when the pH goes from one value to another, it changes color, and it ends up, that tells us the equivalence point. You'll see it looks pretty cool. All right, so let's just talk about real quickly how to read a Buret again. I know you guys have done it before, but it's worth looking at one more time. The first thing to remember is that the 0 is at the top. It's the top line. It's not the very top of the Buret, but the 0 mark is towards the top. In this case, because we're using a 50 ml Buret, the 50 is at the bottom. Next thing is that the closest marks are 0.1 milliliters apart. And remember, what that means is we need to record the volume, any volume we read from this instrument, to 2 places past the decimal. And also remember, we read the bottom of the meniscus. So if this is the meniscus, then we would record this. This would be the initial volume initial. This is going to be 0, between 0 and 1, so 0.7, and I estimate that's about 80% of the way between these 2 marks, but it's kind of a judgment call. So I'd call that 0.78 milliliters. And so that might be our initial volume. We do our titration, which is where we add the sodium hydroxide, which is in here, to the acid, which is underneath it. And when we stop, we read that volume, just the same way we did this, and that's the final volume. So that's how you use the Buret. So we've talked about the first part of the experiment where we determine the concentration of sodium hydroxide in our stock solution by standardizing it. Now in the second part, we use that standardized sodium hydroxide to determine the concentration of our unknown acid. Now the unknown acid is going to be a solution. It's going to look like water. And it's a monoprotic acid, which means that equation that we talked about earlier still applies. It's a 1-to-1 mole ratio between sodium hydroxide and our unknown acid. So the concentration or molarity of our unknown is equal to the moles of our unknown over the liters of our unknown solution. Well, to get the top part of this guy, the moles of our unknown, because it's a 1-to-1 mole ratio, we know that the moles of acid, our unknown, is equal to the moles of sodium hydroxide added at the equivalence point. Well, we know how we're going to determine the equivalence point. That's with our indicator. To get the moles of sodium hydroxide at our equivalence point, we calculated in the first part our average molarity, because in the first part we do that titration 3 times, take the average, and that's what we're going to say is the concentration or molarity of our sodium hydroxide solution. And we know how much we added in this second part at the equivalence point because we measured it with the Buret, our final and our initial volumes. So the volume of sodium hydroxide that we added in liters times the molarity of sodium hydroxide gives us our moles of sodium hydroxide, which is equal to the moles of unknown, which is what goes up here. All we need now, guys, is the liters of our unknown solution. Well, that's really easy because we're going to measure out the volume of our unknown solution with a volumetric pipette. So it's always going to be 10.00 milliliters, or in liters, the volume of solution will be 0.01000 liters. These trailing zeros are important. It's 4 sig figs. That's pretty much what we're going to do. So why don't we go on over there and start the experiment. All right, guys, so this is part A of the acid-base titrations experiment. First thing we're going to have to do is prepare our stock solution of sodium hydroxide. I have a little more than 10 mils of 6 molar sodium hydroxide. For this part, we're not measuring anything carefully. We don't care. So I add this to my 400 ml beaker, and I'm going to add, roughly 200 mils of deionized water. So I'm just going to use the marks on the beaker here. Bring it up to about 200 mils. There's my stock solution. Easy as that. The next thing we have to do is weigh out our KHP into our Erlenmeyer flasks. There's going to be 3 Erlenmeyer flasks. We're going to do this part 3 times. We're going to take an empty Erlenmeyer flask, put it on the balance, tear the balance, because we don't care how much the flask weighs by itself. Take it out because we never add anything directly on the balance. And we're going to put somewhere between 1 and 1.2 grams of KHP in there. And right, 1.153. You guys, everybody's going to have a different number. You'll get your own numbers for that. That's going to be my A1. The second flask would be A2. Third flask would be A3. Now we're going to add about 50 mils of deionized water to this. Don't have to measure it carefully, just roughly 50 mils. Going to add an indicator. So we're going to use bromothymol blue this time. It's called bromothymol blue. When we put it in here, it'll look yellow and it'll turn green at the end point. So this doesn't affect the actual reaction, so the amount we actually put in doesn't matter. A few drops is good. Give it a little swirl. While I'm filling up my Buret, I'm going to put my magnetic stir bar into here, put this on the magnetic stir, turn it on, and let the stir bar start to dissolve the KHP. So now I'm going to add my stock solution to my Buret. I've already rinsed this with DI water and with some of the stock solution. And when I fill this up, I want to fill it up above the top mark, which remember is a 0. There you go. So now I have the Buret full, but at this point there's going to be some air bubbles in the tip, which we have to get out. So this looks like it's pretty much not quite dissolved. I'm going to take a waste beaker, put it underneath the Buret, and open it up. And I don't know if you saw those air bubbles come out, but they did. And now the volume, the level of the stock solution in the Buret is beneath the 0. It doesn't matter where, and we're good to go. That's going to be our initial volume. Set that aside. Put the flask back on the stir. Now we're ready to start our titration. Now, the indicator, bromothymol blue, changes color when we get to our equivalence point. And what's going to do, you can see now, I think that it's a yellow color. We're looking for it to change to about that color right there, a green. Sometimes it goes right from yellow to blue, and that's okay. The point is, we want to be as careful with our titration, with our Buret additions, as we can, so that one drop makes it go from yellow to either green or blue. Now the way we do that with the Buret is we twist this stopcock 180 degrees. The faster we twist it, the slower we go, because we add less with a fast twist. So we can start out, okay, we're gonna need to read our initial volume here, 2 places past the decimal, just like we talked about on the board. And that will be our A4. And then for the second trial, that would be A6. And for the third trial, that would be A8. All right, guys, so now we're all ready to do our titration. We've read our initial volume, 2 past the decimal. We've recorded it. We have our indicator in there. Looks like our KHP is dissolved. So when we start out with this titration, we can go a little bit faster because we know we're not going to be at the equivalence point yet. So going fast with the Buret means twisting the stopcock kind of slowly. So I'm going to go like this. That's a pretty slow twist. And I didn't see any color change really in there, so I can do the same thing. Just like that. Once I start seeing splashes of color that go away, I'm going to slow down, and that means that I'm going to twist the stopcock faster. There, a little bit of color. I don't know if you guys can see that, but there is a little bit of green in there. So I'm going to go a little bit slower, which means I'm going to twist it a little bit faster. I don't know if you can see that. There's a splash of green that's coming in there. And it's starting to last a little bit longer, which means I'm going to go slower, which means twist the stopcock faster. What I'm looking for is one twist, one drop to make it stay green. The first time that happens, that's my equivalence point. Notice I'm starting to twist faster and faster. That's because that splash of color is lasting longer and longer, which tells me I'm getting pretty close to our equivalence point. There, oh, see that? Almost. I'm going to really turn it pretty fast. It's almost there. Not quite. Pretty close. We're looking for this color right about there. So we're still a little bit light, so we're going to go a little bit more. A little bit more, almost there. There we go. That's our end point or equivalence point. So now what we do, record our final volume. So we read the volume, the bottom of the meniscus here on the Buret, 2 past the decimal in milliliters, and that'll be our A5 for the first trial, and then for the second trial would be A7, and the third trial A9. And then we're finished the first part of the experiment. Now we move on to the second part where we titrate our unknown solution. All right, guys, so this is the second part of the acid-base titrations lab, and what we're doing in this part is we're going to determine the concentration of an unknown acid. It looks just like this. So the first thing we do is, as always, unknowns come with unknown numbers, so if you're actually doing this, take the unknown number off and stick it in your data table where it asks for the unknown number. We're going to do this 3 times, just as we did with the KHP. So all we do is we take 3 Erlenmeyer flasks, 250 milliliter Erlenmeyer flasks, and we're going to use a volumetric pipette to transfer 10.00 milliliters of the unknown solution into each of the flasks. I've refilled the Buret with some more stock solution to make sure we don't run out. We're going to add about 50 mils of DI. Don't have to measure it carefully, it really doesn't matter. And a few drops of the indicator, bromothymol blue, and we'll be good to go. So I have roughly 50 mils of deionized water here. Add a few drops, doesn't matter really exactly how many, of bromothymol blue. And just like before, it looks yellow because it's an acidic solution. Pop our magnetic stir bar in there, put it on the magnetic stir plate, and this is just like the first part. We're going to do the titration. When we get to the green color, we stop, making sure we record our initial volume and our final volume for each titration. So the first trial, the initial volume would be B1, and so now we've recorded that, we're ready to go. We're going to start the titration. So just as before, I can turn the stop clock kind of slowly at first until I start seeing splashes of color. Then I'm going to slow down by twisting faster. Starting to see a little splash of color. So I'm going to go a little bit slower by twisting a little bit faster. can see a hint of green start to hang around, but we're looking for this and we're not quite there yet. Keep on going. And that time, we got it. So record our final volume to pass the decimal, milliliters. For the first trial, that will be a B2, and then second trial B4, third trial B6. And that's it. Finish the experiment.